Hello, I'm Jose, and I will be presenting our task overview of the no audio multimodal speech detection task. We are three organizers, Laura Cabrera-Quiros from Instituto Tecnológico de Costa Rica, and myself, Jose Vargas, and Hayley Hong from Delft University of Technology. So I will get into the overview. The task that we have been proposing, this is the third year already that this task runs, and it is about essentially predicting the binary value, that is 1 if a person in a crowded scene is speaking, and 0 if the person is not speaking. Speaking status or speech detection, if you wish, is one of the fundamental tasks in analyzing social behavior and relations, especially when you do it from the perspective of turn taking. You want to know when each person in a scene is speaking, and the automatic assessment of this variable is of course very important, because then turn taking can be related to many other social constructs like rapport and affiliation. It can be used, it has been used in papers that look at, for example, predicting the future of an interaction. Now, if we want to detect a speaking status, then of course we can just give every person a microphone, right? Well, it's in reality not so easy, because there are challenges with giving microphones to people for data collection. There are both technical challenges in that scaling the equipment that is necessary to have high quality recordings in a large crowd, in a large room full of people, can be challenging and expensive. And there are also privacy concerns in that people are not readily happy to give away their privacy. It depends on the situation, of course, but most of the time it can be challenging to have people agree to give their voice recordings. In the case of the dataset used in this challenge, for example, it was collected in a speed dating setting. This is a setting where people normally would like some privacy. So there is actually another way to do this, and that is to not use the audio of the person, but look at how they move when they talk. Use information from their body movement, because we tend to give away when we're speaking by the way we move differently, by the way we gesture, we wobble our heads, or we just tend to move with higher energy. So we can, or algorithms use this to try to learn when people are speaking or not. The challenges are that, well, each person acts differently, of course. We all have different behavior and different ways in which we move. In these short videos, for example, you can see two people doing similar gestures, but the person on the right has much higher energy. The person on the left has much higher energy to their movements than the other person. And we all know somebody, right, who moves with a lot of energy, and somebody who really doesn't. Other challenges are related to collecting data in the wild, where in the picture on the left you can see occlusions. As from this view where the camera is on top and people are crowded, it is really easy to have occlusions affect your videos. And then there's also changing light conditions, both through time and also through the location, so across cameras. The dataset that is used for this task is the match and mingle dataset. This is a dataset that has both speed dates and mingling events that took place over 3 days. For this particular task, we only used the mingling events, where people are talking to each other freely. And we only use the video recordings and the wearable acceleration recordings from accelerometers, like the one you can see in the picture that people wore on their chest, strapped around their neck. And then there were also manual annotations done for many things, among them speaking status, and we also use those. The wearable accelerometers recorded at 20 Hertz, and we have 22 minutes of interaction that were recorded both by the accelerometers and the video cameras. The videos obtained for the same intervals as the acceleration were recorded at 20 frames per second. Then the areas around each participant were annotated using bounding boxes, and then these were extracted and made into subject videos, and these were the videos that were used as input by the task participants. The data was annotated at 20 frames per second also. It was annotated for multiple actions, but for this task we only make use of the speaking status annotations. And these were done from video, so without access to subject audio. We have 3 subtasks. In the first one, we expect participants to train unimodal classifiers, to train one classifier that takes in acceleration and produces a score every second, and to train a classifier that takes in the video frames and produces a score every second. On the second one, we expect participants to train a multimodal classifier, which could be just a fusion of their 2 unimodal classifiers, or it could be something more complex, whatever they decide, and similarly produces predictions every second. And then this year, we are encouraging participants to do an analysis of failure cases by analyzing the subjects who produce the highest errors for their particular implementation. The evaluation was done using the area under the ROC curve, because this is robust to imbalanced classes, which we have to some extent. And then this picture shows how the dataset was divided into training and test sets. As shown, the division was done at the subject level, so the total of 70 subjects was divided into 54 subjects used for training and 16 used for testing. This is because we want to evaluate the approaches in their ability to generalize across subjects. And then there's also an optional set that participants can use to train their person-specific classifiers, or to fine-tune their person-specific classifiers for an optional task. So this year we have only one submission, but we are very happy with that it has quite a bit of novelty with respect to previous years. In particular, for the first time, we have a submission that applies a deep learning method on the video modality. We are quite happy about that. That was something that we mentioned in previous years that we wanted to see. And then we have, for the first time, a submission that applies early feature fusion, which is also something that where most previous submissions had only done late fusion, so score fusion. We now have a submission that looks into fusion at the feature level. And we only have subject-independent results from this submission, which has also been the trend over the 3 years, that we don't have the subject, the participants do not use the subject-specific set, which could be due to lack of space, because we're already asking quite a lot. Among the lessons for the future, we have that the task is perceived as being challenging and unconventional. We think this is also what makes it interesting, though, especially for people looking to apply computer vision and signal processing in the wild. We also have, through the submission from this year, that the video scores, let's say, are closing the gap with the acceleration score. So we are quite happy about where these could lead us to, because in previous years we had that the scores of from the acceleration modality were quite higher than those of the video modality. And I won't spoil the details, but this year the scores are very close from both. And we also think that the complementarity of modalities is something that can be explored a lot deeper. So this would be it for the overview, and we hope that you get the chance to see our participants' presentation. Thank you.